So hello guys, welcome back. Let me see if my voice is working or not. Yes. So welcome back, and yep. So today we'll be discussing the problem number one of IIT MS this year. So I forgot to write 2022 over here, so let me write it down. And yeah, so it's 2022, and now let's see, observe that. Let's solve the problem number one. So it's a beautiful problem. The depth of the problem is in the options, okay? And you will see we need a lot of mathematical jugglery to understand and know the proofs of this problem. Problem number one. So let's see, if you observe the problem asks you the following, that if n is a sequence of non-zero real numbers, then which of the following statements are true? So let's observe this, that we will go through each one of the options one by one. I will show you, okay, at all the proofs and counter examples and everything. And also the best thing is that we will give you some more additional food for thought questions that can be extended out of this question, okay? Some interesting questions that can be made out of this question. So let's check the problem first and see what questions and additional stuff we have on our mind. So it's told that n is a sequence of non-zero real numbers. That's it. Now the first option asks you the following, that if n is n by n plus 1 by n is a convergent sequence, then how does n behave? They ask you the following. So observe, like whenever you have this on mind, whenever they ask you that it's a convergent sequence, always think about what if they're equal, or like the easiest convergent sequence is what? Is a constant, 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 constant. So try to think about that case when an plus 1 by n is a constant. And if you think about that case, if an plus 1 by n is a constant, that case will automatically give you this geometric series, okay? So that is the L. So that will automatically give you that an is equal to L to the power n. So now if you take this series, you will see that an plus 1 by an is a constant, okay? And based on that constant, let's see how it behaves. So if L is greater than 1, so let's say it's 2 to the power n, L is equal greater than 1, let's say L is equal to 2, then the limit will be 2 here, but n will diverge, okay? If L is equal to 1, that is n is all or 1, then the limit will also be 1, okay? And if an is less, like L is less than 1, let's say half, so here the limit will be 0, like the L will be 0, so L is equal to half here. So here this 2 to the power n is going to infinity, here it's going to 1, and here it's going to 0. So it's coming out that depending on this limit and how it's behaving, we have a counter example here, like we have different ways of very like behavior of an depending on where the limit is going. So a food for thought may be in, like, does there exist a general result that, if L is greater than 1, then it will diverge, if L is less than 1, if it will converge always? And so you can think about this question in general as a subjective question, like if L is greater than 1, like let's say limit an plus 1 by n, how does it behave depending on the various values? If it's equal to 1, how does it behave? It's equal to 1, greater than 1, let's say it's equal to 2, how does it behave? Okay, the limit is 2, not the individual number is 2, the limit is 2. So limit is 1 and limit is 0.5. So that's a food for thought question for you from this, that does this mean it always diverges? Does this mean it's equal to converges these two cases? Does it always mean that way? So think about this problem, guys. Very interesting problem, and think about it, okay? So right away we can see it's one will doesn't mean that it will always converge, because let's take n is equal to n. Okay, so it diverges, but n plus 1 by n, it converges to 1. Okay, so that doesn't mean, but does it mean that for half or L less than 1 it always converges to 0? So think about this problem, okay? The problem doesn't mean that you have to, like, since you're solving outside the time regime of the exam, you should think about it, okay? This will enhance your perception about real analysis and how to solve these problems out there. These extra questions you ask yourself make you better. So this is the first one, guys, okay? The first option. And the second option is, let's say, this one, that if n is a bounded sequence, then if is an convergent or not. I mean, if you have done basics of real analysis, you must have seen this result somewhere, that this counter example, this is a very bookish example, like bookish option I should say. So here you know that if an is bounded, does not necessarily converge, just because an can be an oscillatory sequence, okay? An can be really oscillatory in that sense. So an example of an oscillatory sequence is nothing but What? Nothing but plus minus 1, a sine n, okay? So an, if you do an is equal to sine n, so mod of an is less than 1, okay, less than equal to 1, but an is not converging. You don't know where n tends to infinity, s sine n goes. Similarly, for here, if an is equal to minus 1 whole to the power n, an is equal, mod of an is equal to 1, mod of an converges, and mod of an, like, but I mean, it's like bounded, but an is not convergent. So with this mod of an, it's a similar option for the option D, that if mod of n is Cauchy, so you know this result that if Cauchy sequence in R to the power n, okay, in only in certain metric spaces, certain spaces with certain distances only, we can say a Cauchy sequence is always convergent if and only if, only in certain cases. Like in your case, when you're learning real analysis, it's true, but it's not always generally true. Okay, remember that. In real analysis, in your case, it's true. So when it's R to the power n, since it's a real sequence, so here a Cauchy sequence if and only if it's convergent, and mod of an is Cauchy, it's asking that if mod of an is convergent, does it mean it's an is also Cauchy? An is also convergent. So this is the question that is asking over here. So this same example will work. The same example, minus 1 whole to the power n, okay? Because mod of an is equal to 1, but like an is plus minus 1, it's oscillating in nature, okay? So this gives a right away counter example to you that like it's not always true. So we have these three examples quite meticulously done, and this one is really one of the interesting one options out here that can help you learn a bit more. And let's go to the option number C now, okay, the correct option. So it's asking, it's a bit of a long proof, and people will make mistakes in the wrong way. I have seen making people making mistakes in this option, like getting the wrong solution. It's like an plus 2 minus an, like consecutive difference is less than equal to 3 by 4, an plus minus n, okay? So you can observe, you can put n equal to 1, n equal to 2, and see the sequence is coming up. And a3 minus a2 is less than equal to 3 by 4, a2 minus a1. And if you do it, and if you multiply all together, you will see that an minus an minus 1 will turn out to be, all this will cancel with each other, okay? All this will cancel with each other, and only this and this will left. It's called a product telescopic sum, product telescopic. So this all cancelling out each other, and you will see that this term is left. An minus 1 is an minus 1. The consecutive difference of the nth position is less than equal to some constant, okay, whole to the power 3 by 4 whole to the power n minus 2 times a2 minus a1, the initial two terms. Now the basic idea is that from here you can easily say that you can always think that, I mean, 3 by 4 is may not making an option, actually not making a sense, okay, always. So why 3 by 4? Does it can be replaced by something else? So we can tell it from here that an minus 1 is actually going to 0. But does that mean it's convergent? So this is a food for thought question for you. Does an minus 1, if the consecutive difference goes to 0, does it mean that the entire sequence is convergent? We'll see it's not true. Okay, we'll see the interesting example, simple example, it's not true. So we need to actually invest in the time. Like if instead of 3 by 4 whole to the power n minus 1, it was 1 by n, can we say that? I don't think so. So this 3 by 4 whole to the power n minus 2, this format is really, really important for this proof, okay? So let's observe this. So we have got that 3 n minus 1 is less than equal to, so what we do is that we multiply and divide by 3 by 4 whole square, so that it turns out to be n, okay? So we have got this, an minus 1 is less than equal to c times this. Now observe this very carefully. We can write an minus an a1 as a telescopic sum where each individual are getting cancelled like this. An minus 1 plus an minus 1 minus an minus 2 dot dot dot, where each of this will cancel and only a1 an minus an a1 will be left. Okay, this being a tongue twister for me. I hope it's not getting confusing for you. So an minus a1 can be written as this sum. Now we will show that this sum is convergent when n tends to infinity. This series is convergent. We'll show a series convergence. Okay, so what we will show that this series is actually absolutely convergent, and which will imply the conditional convergence. Okay, so we'll show this series is absolutely convergent. We will show this, and it automatically implies this is normally conditionally convergent. And if this is conditionally convergent, it means that this is nothing but an minus a1, the nth partial sum. So it is actually convergent. So it's getting that if we show that this example, if we see this example, we are doing a proof of a convergence using a series convergence. So we are showing an minus 1 as a series, and we are showing it's absolutely convergent. And from the absolutely convergence, we will show it's conditionally convergent. And from the conditional convergence, it automatically imply that an is convergent. So let's see now. I hope you're understanding this. So let's see now how this is absolutely convergent. And you will see the use of this 3 by 4 whole to the power k whole to the power n, that coming up very easily. Okay. So observe that if you add it up, we will now show absolute convergence like this. So observe that each one of them is, we have got each one of them is less than equal to what? This, right? So each one of them is actually less than equal to this times this constant. So we add this up till n. That's really cool, right? And we add this up to 10 and we see n, and we n tends to infinity. And we see that this is a geometric sum. So this is something convergent, this is something positive out here. Okay, this is something bounded out here. So it's a geometric sum, it convergence. Remember, if it was just 1 by n instead of this, we couldn't have said that. Why? Because this would have diverged if it was 1 by n. So since it's geometric over here, this geometric idea, this 3 by 4 whole to the power n, this makes so much sense. Okay, it's not only an minus 1 is going to 0. That's why it's happening. It's because the geometric sum is there, that form is there. Okay, that is super important. It's being reflected over here. So since this is convergent, we can see that this set of the series of positive sequences, sum, all of these are positive, right? Non-negative, I should say. So uska sum is bounded by some constant, positive constant. Okay. Oh, I think it was this. Yes, I think I did yes, it was this. So it's some positive constant. So observe that since the positive constant, and observe this is a series, right? A sum of positive sequences is bounded above. So by Bolzano-Weierstrass theorem, we can see that since the sum of the series is bounded above, each of the partial sum is bounded above. So by Bolzano-Weierstrass, it's an increasing sequence. Each partial sum is an increasing sequence. Okay, each of this is a partial. Let's call it Pn. So we are adding one extra term to it. So it's P1, P1 less than equal to P2 less than equal to P3 dot 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 less than equal to Pn, and less than equal to this constant we have got over here. Let's say L. So by Bolzano-Weierstrass, this limit exists, and therefore this series is absolutely convergent. And since it's absolutely convergent, we can say this is conditionally convergent. And since it's conditionally convergent, we can say that n is actually convergent. Okay, so this is a very interesting, intriguing proof. And observe that this idea is very important. So you may have a shorter proof. If you guys have a shorter proof for this, do share it to us, and it will be like in the comment section, so that people can learn. There may be a shorter way out which I missed. So yeah, so there's a beautiful problem out here which needs some really interesting thoughts, which cannot be done in the exam hall, I believe. So option matching is the way out in the exam hall, but understanding the post exam is really important. So my food for thought questions are the following. So I already given a food for thought in option number A. Please go back and visit it. So my food for thought question is that what if in this 3 by 4 there was some other constant? If it was less than 1, would it have, if it was less than 1, you can see that it would have geometrically convergent. So in this case, it would have been the same thing. What if it was 1? What if it was c greater than 1? Like it was less than 2 to the power n? What would have happened? So that's my food for thought question for you. You can write it down and share it in the comments. So if it's a subjective question, you can write it, upload it in a Google Drive, and share it, share the drive link as a view option in this comment section. I will check it for you. Okay, that's the way we can learn together. And also, what if, this is a very interesting question, what if the consecutive difference goes to 0? Does it mean n is convergent? And we'll see it's not. Let me show you the proof, show the counter example. Let's take n to be this summation of 1 by k from 1 to n. That is n to be this sequence. So observe that an minus 1 is nothing but 1 by n, right? Because 1 by n is added every single time. So observe that an minus 1 is going towards 0, but n is not convergent. An is increasing. You know that this harmonic sum, this is called a harmonic sum. This harmonic sum diverges, right? So an is diverging, but the consecutive difference is decreasing. Okay. So it's like intuitively, it's like a function which goes to infinity, but जिसका derivative is going to zero. And you can see log x is such a function. Log x is a function जिसका derivative is 1 by x. It goes to zero, but itself is goes to infinity. So the rate of growth is high, the rate of growth is going to zero, but itself the function is going to infinity. Similarly, like this, it's a rate of growth, right? Each individual distance. So this is a beautiful idea about sequences and numbers. I hope you enjoyed that. I hope you enjoyed this understanding. And this proof is really important. Many people will miss this proof. Okay. And that's it. That's the beautiful idea about this. And I love this question. I hope you loved it too. And I will see you in the next video, guys. Stay tuned and stay blessed. And if you liked this video, do share, like, and subscribe. And yeah, if you're interested in IIT Jam courses of Cheenta, do see the links below in the description. Thank you, guys. I will see you in the next video. Stay tuned and stay blessed.